This is the second session of the AI series. We will begin now. If anyone has any questions, go ahead and ask us in the chats. Don't forget that we will have a little bit of time at the end for discussions. So feel free to keep your questions till the end.
Elisa, you have to enable me so that I can do the screen sharing.
Yes, yeah.
Okay? Yes, thank you.
Welcome.
Hello, everybody. Welcome back. This is the second session in the Artificial Intelligence workshop. And in this session, we are going to discuss some basic machine learning algorithms. So this is, as we said last time, machine learning is the brain of artificial intelligence. So when you talk about artificial intelligence, you are actually talking about machine learning. So in here, we are going to do some of the basic learning algorithms. These are the neural networks, KNN, SVM, decision trees, and CNN. We are going to see some applications on neural networks. Just a second. So we are going to see an application on neural networks during this session. So the first image we have in here is the neural network. I expect that many of you have already seen this. So the neural network is the actual brain of artificial intelligence. In here we have three basic parts. We have an input layer, we have a number of hidden layers and hidden neurons, and we have an output layer. And the input, we are going to give this artificial brain a number of features so that it can learn through these features, through these examples. And the output layer is the classification. In case we are classifying things, it is the number of outputs that you have. I'm sorry, I don't know what my computer is doing. So in the output layer, I have, in this case, I have, let's say, from 1 till n outputs. So I can have from 1 till n different classes. I'm going to go into a little bit more detail. And here I have one neuron. And this neuron, a single neuron in the brain of the neural network. So in here I have a function of the different inputs and weights. So each input is multiplied by a weight. And then I am going to sum them all up. And I have what we call an activation function. In this case, it is a unit step function. So what a neural network is doing, it's taking all the examples that it has, plus a constant, which is the bias. So I have a function of different parameters and a constant. Each one is multiplied by a weight, and it's going to an output. And we are then combining all of these together to form a network. And this network, so each unit in here is taking all the layer before it and multiplying them by the weights and then summing them up and having a new layer. So if I take an example in here, I have a neural network with 3 layers, an input layer, 1 hidden layer, and 1 output layer. So each neuron of the hidden layer is a function of all the inputs. And therefore, I have in here X, which is the list of the different inputs. X0 is the constant. And I have A, which is the weights. And then I have, A, which is the second layer, and theta, which is the weight. So if you can see, each one of these functions is the multiplication of all the weights with the inputs. And then I have the sum of all of these functions multiplied by an activation function, which is G. And I have the output function H. When you listen to all of this speech, all that you see is just an ordinary function, an ordinary automation function. It doesn't do any learning up till now. The important thing in neural networks is that these weights that you have in here are not constant. These are not fixed weights. These are the actual variables of the machine, of the brain, and they are the variables that are going to be updated from one pass to the other. These are what the machine learns. It learns the weights. Just like when you talk about human memory, it puts more weight into events that happen more and less weight into events that happen less. This is how the creators of neural networks have imagined the machine itself by putting weights and making it similar to the human brain. This is the general function of just any feed-forward neural network. Feed-forward is the thing that I was just explaining, the pass from the input to the output, but it's more general. And here we can see that every layer is the sum of weights and inputs and a bias, and then an activation function, and then another layer, and then another layer to get to the output. Whereas if I'm talking about the back propagation, this is where I am going to change the weights. So I take the output. So I began with a set of inputs, set of features, values of the input. So I take an example, an image, and I extract the features from it, and then I make them enter into the neural network, and then I get the output. But the actual learning of the machine is when I compare this output that I have from my calculation that I have called H, the function A in here or the function H in here, and I compare it with the actual output, the real output that I have, which I call in here Y. And I create a cost, and this cost is proportional between the calculated and the real value. So I create a certain error. And this error in here, we're not going to go into the details. In here, there's a logarithmic between the H and Y, but you can have any other cost function. And then you have this function, which is the new weight equals the old weight and a certain factor and the cost. J is a function of the cost, the sum of the costs of all the errors of all the samples. So, and based on how different are my calculated answers with respect to the real answer, I am going to change the weights so that eventually I get the cost which is tending to zero, the error which is tending to zero. Therefore, the weights that have been calculated, the learned weights, are the good ones that are going to actually give an answer that is very similar to the one that has been given in the sample. So to begin with, I have to define the different parameters that we use or different words that you are going to hear when anybody is talking about machine learning. So when you talk about the data set, this is the actual data that we are using. So the data set has an X and a Y. This means it has the, let's say, an image value and the label of the image value, the input and the output. And the data set is divided into three different parts: the training part, the testing part, and the validation part. The training part is the one we were talking about. We are trying to make the machine learn our information or learn what we want it to learn from the information. Once the machine has learned, we want to test it. When I want to see if the machine has really learned, I want to give it a new set of data, and I want to see how much error does it give if it chooses these weights that it has learned. And then if the test values are give a high error, we are going to repeat the training and so on. What happens is usually if I have a lot of training values and testing values, if I make a lot of passes on them, there is a high risk that the machine memorizes them. This is what we call overfitting. If the machine memorizes the testing values, so it's as if it trains on them, because it sees them, just like when you see an exam too many times, you just know the answers without even understanding the material. This is where the validation set comes into place. So the validation has to be a set that has never been through the train test cycle. If I have a good learning for my data, then I pass it through the validation. If it really gives good results, then the machine has learned. If it doesn't give good results, therefore the machine had what we call an overfitting. It's memorized the data. So I go down to underfitting and overfitting. Underfitting means that the features that you have given are too little, so the machine is not learning. Or any other problem with the model. Maybe the model is too small, it's not learning. Whereas overfitting is when you memorize, the machine memorizes the data. So it's very good, it gives very good results when you are testing, but when you go out to real life, it fails. Classification and regression. Classification is when you want to divide your data into several different parts, classes, like define in different colors, red, green, blue, or when you are going to classify numbers between, or digits between 0 and 9, this classification. Regression is when you want the machine to predict some events or to learn a certain function. So it creates a function, and it can project it to, let's say, future in the time or into values that you do not have. You can have an example where you want the machine to estimate the cost of a house, and you have the cost of a house depending on the different features that are the size of the house, the location of the house, the quality of the building, and different other parameters, maybe the year, because it also changes throughout the history. So you create a function based on these, based on a lot of statistics, and then you ask the robot or the machine to predict the cost of a house in Hawaii in 2025. So it's going to give you an estimation based on learned samples and using the regression function. Hyperparameters are all the parameters that the machine doesn't predict by itself, doesn't change by itself. So we have a set of hyperparameters like the learning rate. So the learning rate is a parameter that is going to adapt. If you have a small value of learning rate, it learns very slowly, but it takes a lot of time. If you have a high value of learning rate, it's going to learn faster, but it could diverge. So it has a high risk of not finding anything. So you have to choose a value of the learning rate which is adequate between the two values. These are usually changed or chosen by testing. You have the percentage of the train test validation parts when you have a data set. So this is another hyperparameter. You have the regularization. This is a hyperparameter. We have it in here. So dropout is a kind of regularization. It means I'm going to reduce the number of, dropout is reducing the number of data that you have, but it's the objective is to reduce the risk of overfitting. Overfitting, we said, is not good because I do not want to memorize the data. I want it to adapt and learn so that it would give good results for any data that it's giving. Confusion matrix is how we see the outputs when we are learning. So if I have, let's say, a classification example with two outputs, I put a table where I have the estimated output and the real output, and I study the percentages. The confusion matrix, we are going to see it later on, so we're going to discuss it later on. And here I have an example where we are going to see a neural network and we are going to work with it. The link that I am going to is a link that you have already sent you before the session. And I hope that some of you have already tested and tried out. And we are going to send it again after the session. And here, this is a neural network. You have the list of features in here, and we are going to talk about them. We have the possibility of adding or reducing the number of layers, the hidden layers. I have in here one hidden layer. I have two input features. I have one output neuron. And I have 4 types of data sets. This is the TensorFlow, they call it playground, so that it's a kind of lab for you to learn how to use neural networks and how to classify, learn what these functions are. So this is the simplest one. I have 2 batches of data. So I'm going to go for a very simple neural network. I just need one output. And if I go for this, I have ratio of training to test data 50%. That's too much. I'm going to take it to 70%. Zero noise, batch size 10. So every time it sends the test data 10 times and then the training data 10 times and then it does the testing. In this example, we don't have a validation set because it is working between training and testing. Some of the machine learning algorithms do not always use the validation set. So if I want to go play from here, I can see the line that is separating between these two, and it already classified it. I can see the error, what they call here the test loss. It goes from a very big error at the beginning, and then it very fast, it stabilizes. I have 0 error now. So it's a very good classification. If I want to add some noise, I will see that because it's a simple application, the machine has learned, but with higher error. And if you see here, you have some blue dots in the yellow part and yellow dots in the blue part, but you have no way of separating them because the error itself is diffused between the two. And this is a case where you will never get a 0 error. And this is very similar to real cases. If instead of taking this sample, I use the same neural network and I go to another, and here I have 2 concentric circles of data, even with much less noise, we're going to try, you see in here, the machine is not able to learn, so the error is not stabilizing, it went to 0.2, it's not able to classify them. So it divided them into 2 parts, but the error is too much. So I have in here a loss which is high. So you would rather go to more neurons. Hopefully in this case, you are going to be able to classify them. So it took some time, but it stabilized, and I have an error that is acceptable. You can see it as well in here that you have a classification, a correct classification of the data. So you can also test it for, you have samples that are more difficult and you can test, you can change, you can play around with this software. This software doesn't require anything on your computer. It is just a page on the internet. So everybody can use it, everybody can test it. If you want to work with neural networks and machine learning algorithms more, if you're interested, I'm going to later on during this session tell you how you are going to do to download these programs onto your computer and work with them. But the simplest way to begin with is to begin with these kinds of pages. So in here, the learning rate, you have different values. So we're taking a average learning rate, 0.03, but you can go to a smaller one. It could stabilize with some values that were unable to stabilize before. The activation function is the one I have showed you in the beginning. So in the neural networks, you have different types of standard activation functions. ReLU is the one that is mainly used, but you have these 4 popular activation functions. You can also change the activation function, and sometimes it does better classification. Regularization is a type of, we said, reducing overfitting. And you have classification. You can also have a regression test. In here we have only 2 sets of data where you can test the regression. So I'm going to go also to some algorithms, but first, do you have any poll results, Elisa?
Yes, of course we do. I'm going to share them with you right now. As
so the question,
shared, yes, I shared the question with everyone through email, and the question was, what is the best machine learning algorithm for image processing? We have 9 answers. 2 of them say that CNN, 1 of them says KNN, 3 say SVM, and 3 voted for decision tree. So now we will see with you, Doctor, the correct answer.
so actually it's the convolutional neural networks that are the most famous for image classification. I'm going in here to discuss very quickly. We're not going to go through the equations, just the method of the different 4 types of machine learning algorithms. So KNN is the K nearest neighbors. So it is the simplest one if you want to think about it. So it takes, if you have already 2 classes of data and you have 1 sample that you do not know how to classify, you take its position. These are X and Y, these are features. And you take, let's say we are treating it in here graphically, and you decide K is a hyperparameter in this case, so it's up to you to decide. If I take K is equal to 3, so I take the 3 nearest samples, and I check these 3 nearest samples belong to which class. If in this case the green class has 2 samples and the red one has 1, therefore my sample goes into the green category, and later on I'm going to use this sample as a green one. So if I have another new sample, I can depend on it to decide on the new samples. Of course, you can go to more dimensions because you can add more features. SVM is what you call a support vector machine. In this image, it is 2-dimensional, but it can go to many different dimensions. I need to draw a line to separate the 2 sets of data. So in here, this data is separable in 2 dimensions. So my line has to be the furthest apart between the samples in the red side and the samples in the green side. But what if my data is like this? So I cannot draw a line. What I can draw is a hyperplane. So I'll have to go add an additional feature to go from 2 dimensions to 3 dimensions. So if this data, I see it in 2 dimensions and unseparable, it could be in another dimension, separable with a hyperplane. So I would divide them into 2 parts using this. And I will always try new features and new ways to be able to separate my data. Of course, we'll always get a minimum amount of noise. In here, we have 0 noise, but it will always be acceptable to a certain level of noise. The decision tree is what we also call fuzzy logic. Instead of having a logic between 0 and 1, I have a tree of decisions. And in here, we have a rather simple example where I have an income range of an applicant, and I want to see if I'm going to give him a loan or no, based on his income and based on the criminal record he has. So if he has a very low income and he has a criminal record, I'm going to give him a loan. If he has a very high income and he has a criminal record, I will not give him a loan. And if he has a medium income, I'm just going to take more and more decisions, and so on. So it's a list of decisions. So in here, this is well, it's the same tree so that you can see it. I have in here years in the present job. If it is less than 1 year, I don't give him a loan. If it is greater than 5 years systematically and between 1 and 5, I'm going to take a decision. This is the CNN. Convolutional neural networks are more advanced than all the rest that I've explained, but they are good in classification. So I'm going to take in here, this is one sample from the data set that we call MNIST. It is a very used set of data to learn classification. This is the digits between 0 and 9, and they are handwritten. So as you can see, we have one of these digits handwritten, this is the digit number 2, which is the input. It is inputted as an image. And at the output, I have 10 classes. These are the digits. So I want to recognize what digit this is. So I go from the first one and I do what I call a convolutional layer. For those who know what a convolution is, this layer is going to do a convolutional function between a filter, which is already the basic, the first values are already inside the system. It's going to take this filter and multiply it all through this image and create a new image, which is something that only the computer will understand. And every one of these filters is going to create an image. So you are going to get a set of images. These are too much of information. Therefore, we do what we call a pooling layer. This is a max pooling that we have used in here to reduce the size of these images, because they are going to be taking a lot of calculation later on if I do not do it. In this example, they have used 2 convolutional layers, therefore as well 2 pooling layers. At the end, we do a flattening layer so that we extract the features from these images and we take them into a neural network. What they called in here a fully connected neural network is a neural network, a basic neural network that was explained in the beginning of this session. And this fully connected neural network is going to give the output. It should in here classify it as digit number 2. If it classifies it as any other digit, it means it's an error. So the weights of the fully connected neural network are parameters, learned parameters, as well as the filters themselves are learned parameters. So I have 2 backpropagation functions to learn. I change the filters that I am doing the convolution with, and I am changing the weights of the last layer. I have, of course, many software, many methods that are dependent on CNN. So you can have RCNN, recurrent, but I didn't explain recurrent networks. So you have many developed methods based on these, but what I've explained in this session are the basic methods. So before I end the session, I just want to remind you that next time we are going to go over some Python basics, because after that I'm going to talk about how to create an environment in Anaconda, how to download Anaconda and create an environment. Then we're going to talk about TensorFlow and Keras. And after that, we're going to talk about, we're going to take an example and apply a neural network, a machine learning, using TensorFlow and Keras. So at the end of this seminar, you are going to learn one example, but you are going to be able to use it. Hopefully, you will be able to do many other examples on your own based on the same method that I'm going to guide you through. I finished my part. This is your part. I want to see if you have any questions or discussions.
Thank
Elisa?
you, Doctor, for this very interesting session. Guys, if you have any question or anything that you would like to discuss, go ahead. You can unmute yourselves and ask anything that you would like. I also would like to ask you to share your video or put an image as your profile picture so that we can take a group photo as we are having the final discussion of this session.
Hello, Doctor. My name is Roy Rasha.
Hi, Roy.
Okay, so I wanted to ask concerning CNN. Is it usually the case used in image processing? Just let me.
Yes, we do use it for image processing. This is what we're explaining. This is the basic algorithm. Between these is the best. Between the ones I explained, is the best for image processing or image classification, if you want.
Okay, thank you. So yeah, this is my question. So it is the underlying process behind image processing.
I didn't get your last comment. Can you raise your voice?
Yes. I said, so this is the underlying process. So it is what happens in image processing. This is the algorithm I meant that's happening under what is done. Yeah.
Well, of course, it's not the only one, but it's one that is a lot used.
Yes. Okay. Thank you so much.
Welcome, Roy.
Everyone feel free to share your video or put your profile image so that we can take a group photograph before we end the session. And go ahead and ask your questions. Dr. Nawal is disposable for your questions.
So we still have 3 minutes if anybody has anything to say or ask.
We have Zainab in the chat asking us about the softwares that we should download later on.
Well, you have Anaconda. This is the software that we are going to use. And within Anaconda, when you create an environment, you get Python inside it. So you don't have to download Python first. And then you have to download the libraries that are TensorFlow and Keras. If you'd like, we could send them in the email that you are going to send.
Yes, that would
We'd
be
add
great.
them to the email.
Yes, that would be great.
Do you have any other questions?
Anyone has any questions about the session or about the future sessions, go ahead and ask before we end the session. We have in the chats, what are the basics we're gonna learn about Python?
Christian, what you're going to learn in Python, you're not going to go through everything that you already know. I expect that everybody who is in this session knows basic programming. I'm going to explain what's different in Python. So I'm going to go very quickly over some basics and see how they are treated in Python. And we're going to talk a little bit of the libraries that Python has, because Python is based on many libraries. Basic Python has very little functions. All the functions are in libraries.
There's someone asking if we are going to use Jupyter and Anaconda. We still have less than one.
We are not going to use Jupyter, but Jupyter is a very useful IDE. But just that I'm going to show you the software that we are going to use in the application is on the internet. It's on a web page, so you can directly open it. And in Google Colab, they internally use Jupyter.
All right.
But you can use
We'll see you
Jupyter.
everyone next week. Session will end now. See you. Bye.